Erucamide is a highly versatile fatty acid amide. In industry, it functions as a critical slip agent for polymer manufacturing, and in the lab, it is widely used in biological membrane research. Today, our objective is to synthesize, purify, and verify high-purity erucamide directly from erucic acid. We will be doing this using an atmospheric urea-based amidation method. Before setting up the glassware, ensure you have the required safety gear. Specifically, a well-ventilated fume hood is strictly mandatory for this protocol, as the chemical reaction produces toxic gases. By choosing this specific atmospheric method, we avoid the hazardous, high-pressure autoclaves required by traditional industrial synthesis. This makes the entire process accessible and safe for standard laboratory setups. This chart details our starting materials. You must weigh out your erucic acid and urea in a strict 1:4 molar ratio. Next, we prepare our catalyst. Mix phosphorus pentoxide and diammonium hydrogen phosphate together in a strict 1:1 weight ratio. The crucial rule for your catalyst mixture is its total mass. The combined mixture must equal exactly 3% of the initial erucic acid's weight. Locking in these exact molar and catalyst weight ratios is what enables the amidation to occur successfully at atmospheric pressure without degrading your final yield. Assemble your reaction in the fume hood using a multi-neck flask. Equip the flask with a mechanical stirrer to maintain agitation and a thermometer to monitor the internal temperature. Make sure that at least one neck of the reaction flask is left completely open or safely vented directly to the hood's exhaust. This diagram shows why we use urea instead of direct ammonia. The upper section reveals urea decomposing under heat to provide ammonia gas in situ. In the bottom equation, this ammonia drives the amidation, producing our target fatty amide alongside ammonia and carbon dioxide byproducts. If the flask were sealed during this step, continuous in situ gas generation would rapidly cause a dangerous explosive pressure buildup inside the glass. Understanding this chemical mechanism highlights why the open vent and active fume hood are not optional. They are required to safely off-gas the toxic byproducts generated as the erucamide forms. Heat the flask mixture to 190 degrees Celsius while maintaining continuous mechanical stirring. Actively monitor the reaction's progress by periodically drawing small samples from the flask and evaluating them using thin layer chromatography, or TLC. Alternatively, you can monitor progress by tracking the steady drop in the mixture's acid value. Do not remove the heat source early. Maintain the temperature until your testing confirms the erucic acid has been entirely consumed. Once the reaction is complete, turn off the heating element and allow the reaction vessel to cool slowly down to room temperature. As the liquid reaction mixture cools, it undergoes a physical phase change, precipitating into an opaque, waxy solid mass. This newly formed solid is crude erucamide. It is heavily contaminated with unreacted starting materials and catalyst residue, meaning it must now undergo rigorous purification before it can be used for research. Transfer the crude solid out of the reaction vessel and into an Erlenmeyer flask. Then prepare hot 95% ethanol to act as your solvent. Add the boiling ethanol slowly, dropwise, only until the crude solid is just dissolved. Using too much hot ethanol is the most common failure point in this step. Excess solvent will trap the erucamide permanently in solution and ruin your final yield. Let the clear solution reach room temperature slowly, then immediately plunge it into an ice bath for 30 minutes to induce crystallization. For the final isolation, vacuum filter the mixture through a Buchner funnel. Wash the crystals exclusively with ice-cold ethanol to prevent dissolving the final product. This recrystallization works perfectly because of erucamide's thermal solubility curve. It is highly soluble in heat and insoluble in cold. This strips away the trapped nitriles and leaves behind only the pure target molecule. Dry your final crystals under a vacuum, then carefully transfer the fluffy white product to a clean, tared vial. We can verify the success of the purification by checking the melting point. This apparatus display shows a sharp, stabilized temperature reading of exactly 83 degrees Celsius. Advanced structural confirmation can also be achieved using an FTIR scan to verify the presence of the exact NH and carbon-oxygen double bond amide peaks. By carefully managing the in situ amidation chemistry and mastering the thermal recrystallization technique, you have successfully bypassed industrial autoclaves to produce research-grade erucamide ready for downstream analysis.